Welcome. Good afternoon. I'm excited to get back to building our compiler in Gleam. If this is your first time on the stream, we're working through this book, Essentials of Compilation, an incremental approach in Racket, but we're using the Gleam language. Gleam is a strongly typed language that compiles to the Erlang VM and also to JavaScript. And it's a great little language. Its syntax looks a little bit like Rust, a little bit like some other things. And it's an interesting alternative to having the kind of dynamic typing that you get from Erlang and Elixir, and LFE for that matter. So I've been enjoying using it, and I think it's really helped with a lot of aspects of building our little compiler. So I promised last time, we kind of left it hanging. And then within I would say 15 minutes to half an hour after finishing the stream last week, I figured it out. and I want to share what I figured out, what the answer to this particular issue was. But I need to set it up. So I'm going to switch over to my editor and show you all what I'm looking at. Okay, so last time we were working on this explicate control phase. So this phase translates something that looks kind of like this, right? Into something that looks a little bit more like C. So there's this L-mon bar, which means it's it has let bindings, and there's no, I forget what the MIDAC form is there, but there are variables and so forth. So this is a functional language with a very simple syntax, and its semantics allow variables and literals and operations, primitive operations. So what we're trying to translate that to is what they call three address code, or monadic normal form. Not monadic normal form, that's this language. I think it's just called three address code, but it kind of has semantics like C. So we have a variable. So following along this translation here, the variable x.to is assigned 20, and it's basically turning this nested functional structure into an imperative sequence of assignments and operations. So here, x1 is assigned 22, and then you add x2 to x1, and you assign that to y3, and I messed that up, you return y3. So that's what this transformation that we're working on, or that we were working on last week, was trying to do. The thing that we were stuck on is this has two functions. So there's explicate tail. So this means that if an expression is in tail position, in other words, it is like the root expression of the functional language, or it is the last expression, say, for example, in a let. So that's what they mean by it. So if there's a program that has a root expression E, that E is in tail position. Or if you have a let expression, then where it's like let x E1 E2. So let Y3, this is E1 in here, this is E2, then E2 is in tail position as well. And this is about unwinding the kind of nested recursive structure of the functional language into this flat imperative structure that's kind of a sequence of instructions. So that in this case, y3 is the thing that's going to be returned at the end of this. So the realization I had, and the problem we were running into is, it makes complete sense to go, if we have a let expression in tail position, then we know that E is in tail position, so we can recurse into the transformation for tail on that. But then we go into explicate assign, because in order for this expression to be valid, to have all the variables it needs to, to perform it, we have to evaluate b, which was the right hand side of the let. So so we go into explicate assign b, and v is the variable name it'll be assigned to, the result of b, and then tail. So we're trying to, since there's not really, it's not really flat, we're expressing it as const cells. So if you look at cvar, this tail expression is either a return, so that's like return y.3, or it's a sequence where you have a statement and another tail. So this is a self-recursive data structure, meaning that the only ways that this can grow are to add more statements on the front that are followed by another tail, or to return an expression. So over here, when we're doing explicate assign, we know that the result of explicate tail for e is a tail expression. So it's either return or it's some amount of nesting of sequences. And then what we're trying to do is add additional sequences on the outside. So it's like a const cell in a list, like a functional list, where you have head and tail. And we're just creating more heads on the front, wrapping the tail. So that's the thing that gets confusing is that we are figuring out what the tail is first, even though logically that comes later in the program, right? So that was what was kind of bending my brain. And they do call this continuation passing, except the continuation is not a function, it's an expression. Like it's syntax, it's AST in this cvar language, right? Okay. So that's all well good. We're like, okay, so we can figure out how to do a let when we're in tail position. What got confusing is, well, what if we have a let that's not in tail position? And here's the answer. But so, for example, if you look at this, this outer let is in tail position, but this let is not, right? This let right here is nested inside, and the result of this is going to be eventually assigned to y3. Okay. So what can we do about that? Well, what got confusing was we're already evaluating an assign here. We're already trying to figure out how do we bind the variable that the tail here needs in order to continue. Well, if these were simple expressions like, oh, you had either a variable or an integer, then that's easy. You assign that variable to whatever that atomic expression is, and then you continue, right? So it's create a sequence where there's another assignment. If it's the read expression, then or if there's any of these primitive operations, then you do the assignment there and so forth. And so the primitive expressions or primitive operations were easy to figure out. Because it was a single assign, right? So read, which is read from standard input, negate, which is flip the sign of the integer, minus and plus. But when we got to let, it was like, okay, so we have lets on lets on lets, and it gets really confusing. So I kind of wrote it out as this is the form that we want. So if we are matching a let where this is the right hand side of an assignment, right? We've come in here with explicate assign b, which is the expression, v is the variable to assign it to, and e is what we want to pass next. I'm sorry, so cont, so we have expression, v, and continuation, cont. So the form that we want is that we evaluate the inner let. So we assign v1 to whatever the b is in here, the block of code. And then we evaluate E, right? And we assign that to V. And then we do the rest. So this is the form I was trying to create. And the thing about tail position is we can't treat E like it's in tail position because it's not. So the answer was, like we were doing above, so we could say this is tail-ish. I just put it in line. But you could say, okay, similar to how we did up here, where this is explicate tail and explicate assign, since we're not in tail position here, we have to do explicate assign again. So we do explicate assign on E. That's the continuation, except that note that this continuation is what follows the evaluation of E. So that has to go into this spot. And we already know it's a tail, so that's the only place it can go. And since explicate assign returns a tail, that can go into this explicate assign. So it's kind of like we're doing a double wrapping. Anyway, if we run the tests, they do pass. Here's the test that I wrote. I think we wrote some of these last time. So here was the example that we had up above in our other file. And so it was, let y.3 is assigned to this expression. And then, our return is return y.3. And then there's all this inner stuff. And so what that, and I think we went through this last time because we were like, we know this is what it needs to look like. So in order for this to be evaluated correctly, it has to assign the value of x.2, which is this inner bit. We know that that's atomic, so that's assigned to 20. Assign x.1 to 22, and then assign y.3 to the primitive operation of plus x2 and x1, and then finally return y.3. So even though this is nested, you can kind of think of it as this is a list of assign x.2, assign x.1, assign y.3 to this result, return y.3. So that test pass, and I think that we'll go ahead and commit this because I want to move on to the next section. So that was the explanation of what I figured out. Let me save. And you know what? We're going to try. I haven't used it that much. There's a new Git UI for Z. Yeah, let's stage all. So this is chapter 2.6, explicate control. And we'll commit and we'll publish. That's pretty easy. Okay. So now we have that updated. And we're going to move on to 2.7. So 2.7 is called select instructions. In the select instructions pass, I'm reading from the book here, we begin the work of translating from CVAR into x86 var. Okay, so we have x86 integer, but nothing with variables. So it sounds like we're making a new intermediate representation. So the target language of this pass is a variant of x86 that still uses variables. So we add an AST node of the form var to the arg non-terminal. Okay, so this is the arg non-terminal. Basically, we'll be adding a var. I think a little for type safety, I doubt that they expect you to do this in the Racket version. I think for type safety, we're going to make a new one, and we'll call it x86 var. And we'll just copy this in because it's fine to have that. And var is going to be string. Okay. So they say we recommend implementing select instructions with 3 auxiliary functions, one for each of the non-terminals of CVAR. So for this, there's atomic, ATM, and statement, right, and tail. Okay, so let's get started. We're going to make a new pass, and this is called select instructions. And again here, yeah, so they have this CVAR to x86 var. And we're going to put this in here in the top. So this is what our pass is. And then we're yep, pubfun. Okay. Sorry, I had to remind myself of syntax. So we're going to call this select instructions. And this is going to take input is a cvar.program, C program. We need to import lang cvar. Okay. And this is going to output x86 var. Is it x86 program? Yeah. Okay. Okay, we'll put a to-do in there for now. Okay. So, the cases for atomic expressions are straightforward. Variables stay the same and integer constants change to immediates. So if we say, we'll just call this select ATM. It's not public though. And this is going to take a cvar.atomic. Right. And this is going to return an x86 var.arg. Okay. Let's do exactly what they say. So for an integer, so int here, that's going to be an int. So for that, we can do immediate, as they say. And then for variable, we add a variable. Okay, that's not hard. Okay, so let's consider the cases for the statement non-terminal. I think what this should be, because note that we have block is a list of instructions. I think what we should be returning here is a list of x86 var.instructions. Okay, that's just complaining about it not being used. So, and then, you know, we'll put a to-do here also for this one. We'll come back to it. We also need select tail, which is going to be a cvar.tail. And that's going to be a list of x86 var.instruction. Okay, so let's get Gleam list in here. List, because we're going to need that. I think it does have the plus plus, but we're probably going to need something from there. Okay, so let's match on tail. Or let me read a little bit back, and then we'll go into each of these. The atomic was easy because those are only in argument positions, so it's not hard. Okay. So consider the cases for the statement non-terminal starting with the arithmetic operations. For example, consider the following addition operation on the left side, which is var equals plus atomic 1, atomic 2. There is an add q instruction in x86, but it performs an in-place update. So we could move arg1 into the left-hand var, and then add arg2 to var, where arg1 and arg2 are the translations of at atomic 1 and atomic 2 respectively. So they're saying if you had var, I'm going to type this up so we can see atomic 1 and atomic 2, you want to translate that to move q arg1, so that's a translation of that to var, and then add q arg2 var. That's what they're suggesting. Okay. There are also cases that require special care to avoid generating needlessly complicated code. For example, if one of the arguments of the addition is the same variable as the left-hand side of the assignment, so var equals plus atm1 var, then there is no need for the extra move instruction. So they're saying that should translate to add q arg1 var. Okay. And then finally, the read operation does not have a direct counterpoint in x86 assembly. So they provide a C file that you can link in with the function readInt in it. So that if you have var equals read, then that should translate to call q readInt and then move q rax var. Okay, so that's statements. So statements we know has only one variant. Only one variant. There's only a sign, right? So technically we could probably pattern match this a different way, but assign, let's see. Assign has a variable and an expression. Okay, so what we need to do here is this expression. We need to explode the possible values here, and then probably explode the possible values on primitive. And I think that will cover what we want to figure out. So let's throw in like okay, so now we're going to go over here and see if we can't oops, add missing patterns. Okay, so for this okay, I'm going to hold on that, and then we're going to do like plus, and then let's get this. Let's see, V. Let's get this to be fill out the rest of the missing patterns. Okay, except we are also probably going to need to deal with the case where V yeah, I mean, I'm okay with exploding the cases a bit more here. I think let's go ahead and do the easy ones first. So I'm going to move read up to the top, and we'll also do the atomic one. So for this, what we'll do is we'll have x86 var move q. Did we not add variable? Sure we did. Yeah, so that's an argument. Move q takes 2 args. Okay. So that's actually going to come last. And we'll say a select ATM of ATM there. Okay. So this is a simple move the whatever value this is into that variable. Okay. Let's do read. This one is simple from the book as well. So this is call q. And what is that? Arity and label. Label arity. Okay, so label is going to be read int arity 0. And then we'll have move q. And we're going to do register. And that's going to be RAX. Into our variable. Okay, except we need V here. Okay, do those make sense to everybody so far? So if we have either a variable or an immediate value, like an integer, then we just put that into this variable spot. Okay, if we're reading one from standard in, we call the readInt procedure, and then we, since it's going to put the integer that it read from the command line into RAX, then we can't take RAX and put it into the variable. So this is sort of how we're taking these abstract assignments and turning them into a skeleton of the x86 instructions. Okay, and then I'm going to, oops, where we go? I'm going to move, oh, I'm using command, not alt. Okay, so I'm going to move neg up first because it's also going to be easier than, excuse me, than plus and minus. Okay, so that's a primitive operation, and it should only take an atomic, right? Right, so that's an atomic expression. So what we can, here's where we need to get a little bit creative. So let's see. So I'm duplicating that line. And I think what I'm going to do is this first one is going to be as variable. So if these two match, duplicate variable, okay, so we have to put a guard on that. And I think that's because, you know, if this were Erlang or Elixir, I would just say those are the same variable, and that would be treated as a match. But because Gleam can compile a JavaScript which doesn't have this kind of pattern matching, we have to have a guard on it. So we'll be seeing this in a couple other statements or branches of this function here. Okay, so if we're trying, if v1 is the same as v, this is that operation or that optimization they were talking about, where you really only need one instruction here. You don't need to do any moves. So in this case, we'll do negq, and then that's going to be okay. So we've just figured out that, you know, if we're assigning v the negative of v, then we can just operate directly on that. Now, if it's anything else, then we have to do I'm going to do this as a move. Of into our variable, followed by this, right? So if we are assigning v the value of the negation of ATM, then we move that into v, and then we negate v. Simple enough. Okay, so now we can duplicate this pattern. It's going to be a bit more verbose for plus and minus, but once we've done one of them, the other one will be just like copy, paste, modify, right? Okay, so we need to handle the case where this is, so the left-hand side and then we'll add another case where it's the right-hand side. And then we'll add the final case that it's neither of them, right? Okay, so if what we're trying to do is add b to v, then we just do this, ATM b, right? Because we know that's atomic. And then we, excuse me, goodness. And then we assign it to the variable. So put it in there. Okay. And now we'll do the same here, except we'll do A. Okay, and now here's the where neither of them are a reuse of that variable, right? So in this case, we'll do what they suggest up here, which is this move q add q sequence. So we're going to move the value of a into the variable v, and then we're going to add q of b into the variable. Okay, so now we have this pattern, and we can basically duplicate it for, excuse me, for minus. So let's do this and get this, and then we'll duplicate that, and we'll go, I hate it when I miss. I hate it when I miss. And then finally A and B. And remove the guard. Do I have too many parens there? No, they're just complaining about it being unused. Okay, so here we can basically do this, except it's going to be sub q, right? And I need to make sure that we have that bound on all of them. Okay, and then similarly here, except it's A. So you can see that, you know, as we figure out what the problem is, the solution gets quite mechanical. So that's a good thing. Okay, so now we have, I think we've covered basically everything that can happen in a statement. Remember, a statement is just assignment. So assign a variable the value of some expression, and an expression is either, you know, an atomic item or a primitive operation. We've covered the primitive operations. We covered the atomic values by that other function select ATM. Okay. So now we need to deal with the tail. Okay, so there are two cases for the tail non-terminal: return and seek. So sequence. Regarding return, we recommended treating as assignment to the RAX register, followed by a jump to the conclusion of the program. So let's go ahead and make our case here. Case input. Add the missing patterns. So return can contain an expression, right? Right, so we'll need to handle all the possible values of the expression. And then the sequence, you can translate the statement S and tail recursively and then append the resulting instructions. Okay, so this is why I brought in the list module, because we'll probably want to have some kind of append there. Okay, so this is, let's put this up because I want to handle that. So we'll do select statement on S, right? Let's see what's in the list dot append. Yes, there's a list module, and then we'll do list append on select tail of T. Okay, easy enough. Now we just have to, because we already did all the hard work up here, right? Now we just have to deal with the values of return. So we know it's going to be a list. The question is, you know, this has to be expressions. So what we need to do here. Hello, Isaac. Your minus has an unintended swap in one case. Yeah, let's think about that. Right, because the add is commutative, subtract is not. So right, so we want to, so that it's this one, right? Because you're subtracting the variable from A, so this needs additional instructions. Because this is atomic, it could be an immediate. We can't put this on the right hand side of the subqueue. So maybe we only care about this, optimizing this one, and this one can be actually we would have a conflict there, wouldn't we? Because if this variable is being reused, I think feels like we need to introduce a new variable there, doesn't it? Because if we move the value of A, oh, I know how we can get around that. I think we could negate A and then add. No, wait, that's not right. We would negate V1 and then add QA. Yeah, let's do that. It's not optimal, obviously, but we won't have to introduce a variable. That was my main concern. Thank you for calling that out, Isaac. Also, new handle. Thank you. So, yeah, otherwise we would be in a situation where we could overwrite V with whatever the value of this expression is. I'm sorry, this atomic. And then we wouldn't be able to subtract it anymore. So I think that this is probably the way to go. Thank you for calling that out. And we couldn't go to this one because then we wouldn't know if it's the same variable. Okay, cool. Thank you very much, Isaac. That was helpful. Right, okay, so if we're returning an atomic that's either a variable or an immediate, so they say jump to the conclusion of the program. So the conclusion needs to be labeled, which they do later. So let's do this case. Let's do commenting from friend watching on TV. Okay. Thank you for alerting me to that problem. Okay, so we're gonna move this atomic into a register RAX. And then jump conclusion is what we're calling it. Okay, So now it's going to be like, oh, you haven't filled out the other options. So let's go ahead and do that. Add missing patterns. And then we're probably going to have to explode these again, like we did before. And let's see. Well, we don't have to deal with the assignment because there's no assignment. It's just this part. So let's go ahead and do cvar.read. And then we'll explode this again. Add missing patterns. Okay. So for this, we're basically going to do, except we don't have to move it at all. This feels like a dumb case, but so we know that in this case, if you're just doing return read, we know that readInt already puts it in REX, so we can just jump to the conclusion after we've called readInt. All right. So for these cases, let's go ahead and get, I want to get the simple ones up above. Okay, so for negate, we know that's an atomic, so we can move that. And since we're going to be returning in REX, there's no point in doing anything but that. So we're going to move that atomic into REX. And then we'll jump to the conclusion. Okay, and we've got A and B here. So this is sort of like repeating a bit what we have up here, except we're using REX as the variable. Move Q. And we're going to be copying this a lot, so bear with me. And then we'll do add Q. Okay, and then you know, minus is basically this, but we do sub Q here. Okay, and I think that handles all of our cases. So what we want select instructions to do is take a CVAR program and return an x86 program. So let's wrap all of this up. So what do we have in here? I think we weren't setting this. Okay, so we need to do like a fold. Let's not use that. Import Gleam dict. So we want the x86. This is going to be a dictionary of strings, so labels to blocks. And a block is a list of instructions. So what we have so far is this list of instructions. Neg does a move, if I catch it correctly. I'm not sure which part you mean. Neg Q? Or the one in CVAR? Or are you talking about down below? Like here? Oh, I see what you mean. we were missing a step here. Yep, thank you. Thank you for calling that out. It's easy when you're doing this repetitive stuff to miss something, so thank you. Okay. Yeah, I mean, it does need to do a move to get it into RAX, but we forgot to do the neg queue. So thank you for calling that out, Isaac. Okay. All right, so we're going to do... So we need these CVAR like labels to become the labels in the x86 program as well. And I think that we had, yeah, so we have a dictionary there. So let's pull up a browser here, Gleam standard lib. Oh, wrong one. Gleam standard lib. Let's look at the dictionary. So I think we probably just want map. If there's a map function, map values. Yep, and we can ignore the key because we want the key to be the same. Okay, so let's say blocks is dict.mapValues, and we're going to take input.body, and then we're going to make a function, and we don't care what the first argument is. Actually, what we can do is just call this select. Select tail. We can't use it directly because that takes 2 arguments. I don't know if I need to put types on that. Probably. Okay, so of course we didn't return that. So we need to make a program. And that takes blocks. All right, so what's wrong here? All right, so we need to construct a block around that. Okay. Hopefully that's clear enough. I'm glad I didn't have to put in the types on all of those things for that closure. I actually wish that there were a shorthand for that, for ignoring the first argument. But I don't know if Gleam has that sort of thing, like Haskell does, obviously. But okay. So now let's write some tests. Oops. Select instructions. Oh, oops. Rename that. Select instructions test. Okay. Cool. So we'll copy, some of this stuff. So we need Glee unit, and we're gonna need CVAR, and we're gonna need x86 var, and we're gonna need to import select instructions. Yeah. Okay. All right. So I would like to take what we were doing from explicate control test and then figure out what this will look like. So if we think, let's do this. Select instructions test. Okay, so we have our C program. C, let's call it x86. Okay, and let's let our x86 program be okay, so I'm sorry, that's going to have start is going to be the symbol, and then that's going to have a block and a list of instructions. So now we can go figure out what we think this should be, and then we will do the C program pass to select instructions should equal the X program. Okay, we know that this will fail. Like, we can run it right now. Yeah, it fails. Oops, I need to make that pub. Let's try that again. Right, so I'm not going to look at the answer. I want to kind of like work my way through it and see what I would expect it to be. Okay, so sorry, I'm moving the book out of the way. Okay, so we have x86 with variables, so we could work our way backwards, but I think, or we can go forward. So let's do. I'm going to expect the first one is going to be. We're going to have immediate of 20 put into var of x.2, right? And then we're going to have an immediate of 22 put into var x.1. And then we have the plus. So I think we're going to have a move of x86 var. So it's going to take this one first. So x.2, y.3. And then we're going to have an add queue, right? x.1, y.3. Okay, so then we've done the add. And then we're going to return y.3. So then we'll have a move. So remember that these are abstract locations. They're not actually something that the x86 could execute yet. So bear that in mind. And then we'll have jump conclusion. Does that seem reasonable? Based on this thing, this is what we would produce? I think so. Note that we don't have conclusion yet. So that's, you know, there's some extra work here that obviously this is not optimized, right? Like a you know, a future pass might go through here and do lifetime analysis or data flow analysis on these locations and go, hey, like we're putting x2 into y3 down here, so we can just put this into y3 and then add x1 to it, and that cuts an instruction. But we're not going to do that. Also, we know that y3 is going to go to RAX, so we can just assign y3 to RAX and replace all the places where y3 is referenced with RAX. That sort of stuff. But we're not doing that yet. Okay. So let's run this test again and see what we get. It passed. So I guessed right. And I feel pretty good about that because I can look at this and go, this looks correct. Now we probably need to cover some more cases. So maybe we should look back at some of the other tests that we've done. That one's not particularly interesting. The uniquify, remove complex operands. I think given the fact that I messed up the negate twice, and Isaac caught it, we should probably test that. This is the one we did. So let's do select instructions, negate, test, okay, and then we'll construct a program. Okay. So let's come up with one. We want something like let x1 is we'll do this one. So maybe let's figure this out in the CVAR language. So we have a sequence, assign x.1, that takes an expression. So Atom int of 42, and then we have a tail, which is except we will have removed complex expressions. Complex operands. Right, so this maybe what we do is let's do this. All right, what can go? Oh, I'm sorry, c.seek. We need another sequence. You know, the other thing I could do potentially here is put this into our other phases and have it output something in CVAR. Yeah, let's forget the let, and let's just say this is plus 42, negative 10, negate 10. And so we will do like a pipeline. We can go through each of the phases. Yeah. Excuse me. So we're gonna import that. Program plus, this one is going to be significantly simpler. Oh, I'm sorry, prim, or primitive operation, plus, and this is going to be an integer, 42. Okay. So let's see here. If what do these do? So we would start with uniqueify. Look back at the diagram, make sure I'm doing that right. Yeah, uniqueify, then remove complex operands, then explicate control, then select instructions. So we're testing select instructions. So we'll do uniqueify, remove complex operands, explicate control. And we'll just pipe those together if we can. So let's do that. And we're going to pipe that to uniqueify. And we'll pipe that to remove complex operands. And we'll pipe that to explicate control. And then what is the value of that? That's a C program. So we don't need to do this. So let's just do CP. Okay, so now this will introduce variables, remember? So I think we have a test for this. Right, so it turns that negate 10 into temp.1. So I think that what I'm expecting here is program. Dict from list. Start. And we have a block which contains a list. Excuse me. Okay, so given this, we're probably going to have again, we're guessing here. I think we'll learn. Immediate 10 into a variable. I'm thinking it's going to be temp.1. And then we're going to negate. And then we're going to probably just add. (42) into that. And then we'll move into REX. And then we'll jump. Conclusion. That's what I would expect it to generate, but we'll find out. And then let's put this. All right. And then I'm going to go big on here. Okay, so we got interesting. Okay. So it put you can see here the difference. It put the add in tail position. So that was like return this expression. So this is where we got it wrong. And this looks correct. It didn't add 42 back to that variable. It moved 42 into rex and then added temp.1. So that makes sense. And let's see here. So we know that it got the negation correct there because it moved the variable, this value into the variable and then negated the variable. So yeah, I think that mostly covers this, except what we're going to do. Okay, and then that's pretty good. And we don't need this additional move. Wait, hold on. Okay, so this is rex, but this is a move queue, right? And this is add queue. Okay, so that does match what we expect. Good. All right, cool. We have at least 45 minutes, maybe some more. Let's get a commit on this. We're adding that, and these are new. And this is chapter 2.7, select instructions. Okay. So our next step is called assign homes. This is section 2.8, chapter 2.8. The assign homes pass compiles x86 var programs into x86 var programs that no longer use program variables. Thus, the assign homes pass is responsible for placing all program variables in registers or on the stack. For runtime efficiency, it is better to place variables in registers, but because there are only 16 registers, some programs must necessarily resort to placing some variables on the stack. In this chapter, we focus on the mechanics of placing variables on the stack. We study an algorithm for placing variables in registers in chapter 3. So I think that this will be fairly straightforward. The question is, do we treat this as a transformation from var, so the x86 that has variables, to the one that doesn't? Or do we just treat it as, oh, well, you can no longer have this kind of arg? And I think if there were a straightforward way to go, well, just this type is substituted, I would go for it. But I think we might need to go through the steps of dealing with the removal of var, and translate from this into that. The question is, okay, the next phase. Oh, well, they're saying stay in var and then go to the int version in the next phase. I guess that's fine. The challenge is we might want to have an additional pass where we validate that none of the arguments are vars. They're all immediate reg or deref. The thing is, like, if we've already got that here, why don't we just remove it? I don't know. I'm kind of on the fence. And there's also a possibility that they've made updates to the book since this printing that address this particular issue, but they might not have because it's in Racket. Like, you're not required to have the same level of type safety that you do in Gleam. So we're kind of, again, like, I'm really enjoying this exercise, but we are a bit going off the reservation because we're not using Racket. So there's an additional potential for divergence here where they were just like, yeah, it doesn't actually matter. So I like the idea of assign homes going to, because the only difference is this variant, I think going to assign homes having to do the translation here is fine. Because we're either going to have to do it here or we're going to have to do it in the next step, the patch instructions step. And I don't know that that's like, I don't know that that's the right step to do it. The other argument could be that, like, what patch instructions does is that it ensures that that there's only one argument to each instruction that is a deref. Because you can only have stack locations in one argument of the two. So I could see either one. But let's do it in assign homes, and we'll have less pain in patch instructions, which I think is going to be a little bit gnarly. So, okay, so we're going to make a new phase. So assign homes. Yeah, replaces variables with registers or stack locations. Okay. So assign homes. Except we're gonna do int here, and then we're gonna adjust their thing to be from int to int. Okay. So this is assign homes, and the input is going to be import langs x86 var. We're going to call that var maybe, and import langs x86 int as x86. So okay, and this is going to return an x86 program. All right, so I think what we're going to do is this. We're going to do map values again. Yeah, I thought about it a lot, and like it's not strictly necessary from a procedural step to make sure that you have no variables. I mean, you can do that with the code rather than the types. But since the patch instructions step has to have no variables, like I don't see why we don't translate it here. Okay, so we're going to take input.body, and this is going to take the key and the block, and we're going to do assign homes block. I'm sorry, I need to do, we're not specifying the type, so you don't need the arrow. And then we'll do Okay, so this is sort of what we did in the other module. So, and I think that probably what we can do take block, assign homes block. I'm going to do it like this. Block dot. What is the contents of that? Block dot body. And then we'll pass that to x86 dot x86 block. So we're just doing like a extract, go over the list of instructions, and yeah. So assign homes for block. And this is going to take, its input is a list of var dot instruction, and it's going to produce a list of x86 dot instruction, right? Okay. And we're going to need list map again. So we'll probably need fold, actually. So we're working with a list of instructions here. That's the contents of that block. Let me put to do in here for now and let it reformat. Right, so block is a list of instructions. So we need to go down into each of these instructions and find any arguments in them. So let's, and I think it's probably best to do that with list map. No, but we need some kind of accumulator, because we need to know what we need, like a mapping, so it'll be a dict of a variable to a stack location, or rather that's like a what is it in here? It's a deref, right? So we'll construct the arg. So a map of a variable name to an argument. So that's a string. Okay, so then when we encounter that variable name again, we can I make a new function here. This is going to take a name, a string, and the other thing that we're going to need is like, what's the max? So maybe this thing is we're going to say type homes is going to have it's going to have a counter. So like, let's say offset is an int, and then we're going to have the homes is going to be a dictionary of a string to x86 arg. Okay, so yeah, so here we're going to take this and homes, so the existing homes, and then we're going to return an arg and a new homes, right? What I'm trying to do here is like, if this, we're trying to extract the idea of where is this variable? Do we know about it already? If we do, we'll just return that, and the existing thing. But if it's a new variable, then we need to give it something based off what our given offset is, and then return that. So this is x86 arg. Okay, so we're gonna do so if there's, what are the arguments to this? Get takes the dictionary and the key. Okay, if there's an error, which in this case it's always error nil. Nil is the type. We don't care what that is. So then we'll do deref. So we want RBP, and then we want negative, let's say let new offset homes.offset plus 8. So, or actually we just subtract 8. Oops. And then we give it new offset. And then what we're going to return is this is the argument, and we're going to construct a new homes, and we're going to give it new offset, and dict.insert homes, and that's going to take the name and the arg. And then if we do get it, then we just return arg and homes unmodified. Okay, so here we're constructing, and let me explain a little bit about the dereferencing. In their examples for this section, so if you have, let's type out one of these examples real quick. So they're saying if you have move q 42 to the variable a, and then you have move q a to b, and then you have move q b to rax, what they want this to become is move q 42 to negative 8 RBP. So this is, remember the stack grows down from the top of the memory region. So as you add things to the stack, you subtract addresses. And RBP is the base pointer to the stack for your current frame. So they're like, you know, subtract 8 from that for a slot for A, and then they do move Q of negative 8 RBP to negative 16 RBP. And then they're doing move Q of negative. So this is kind of pointless code in a way, but it's useful for showing the translation, that when you encounter a new variable, you subtract from the stack offset, and you use that as a dereference on RBP. So A exists at this point, they moved here. Okay, try to figure out what the argument is here. A, you already know that it's negative RBP, so stick that in there. And then you go to this step, and oh, you know, this is a new variable, so subtract 8 again, you get negative 16 RBP. And then you go down to this expression, or I'm sorry, this instruction, and you look up B, and it's negative 16 RBP because you just assigned it there, and so forth. So that's what we're doing. It's a really naive allocation, really, for each of these variables. they're talking about some things that are not part of this yet, um, but are existing in their support code. We may have to go back at a later time and fill those in. They're talking about the types of local variables. We're not caring about that right now because there's only one type. There's just integer, right? So we're not really doing anything with that. Okay. So let's see if we can do this. We're going to start with we're going to make another function, I think. Yeah. Maybe. Let's look at the list module in the standard library. Yeah, I think I want fold. And we definitely want left to right. We don't want right to left. So a fold over list from the initial B with, okay. No, it takes the accumulator as the first argument, not the item. Okay. So let's make a assign home instruction, and this is going to take homes, which is this, our accumulator, and an instruction, which is going to be a var.instruction. And what we want to return is yeah, that's not exactly right. We have this inner thing. So this is actually fine for our inner loop. Yeah. And we'll do something else for the outer part. So this is going to return an x86. Let's have it return the homes first, and an x86 dot instruction. Oops. Okay, this is our we've got a to do here, and we're going to do something like list fold over. This is the input, and we're going to have think about how to structure this, because we've got this accumulator that's keeping track of where our variables are, but we also, what we ultimately want to return is the list of instructions. And we want to throw away the homes. So I think we do, and then whatever goes here, and then we return instructions. So we need to keep, the accumulator is going to have so we start with an offset of 0 and a dict new. Okay. And then our function is going to take and the individual instruction, right? it takes the accumulator. Oh, wait, this needs to have an empty list in it. Okay. So what are we looking for here? Right. So what we want to do is get we can do this in reverse order, I guess. Yep. We could do it in reverse order. Is there a reverse in here? Yeah. This is not something that you care about on JavaScript, but on Beam, it's more efficient to when you're looping over a list in some form or another, you write it out in the order, like adding on the front, and then at the very end you reverse it, and that reverse is heavily optimized in the virtual machine so that it's not chasing as many pointers as you think. Yep. Okay. So we're going to go new. This is going to be new homes, new instruction. This is going to be assign homes instruction for and here's where I wish I had a pattern match on that. We can go homes instructions is accumulator, and this will take homes and the individual instruction, and then what we're going to return is new homes, and we're going to append new instruction on the front of instructions. Is that not how you do it? Oh, you do like this. Okay. Interesting. Okay, so that's basically what our thing does, and now what we need to do is look at each of these instructions. So we're going to do case instruction, and let's add the missing patterns. So this is going to be x86 retq. We have to handle this even though we don't have it in any of our programs yet. Location, this is right, and in these cases we don't change the homes, so we can just return homes in the instruction, the translated instruction. Okay. This is also unchanged, so this is label arity. Call queue, label arity. All right. So I think that we're, I thought we could use this directly here. We're probably going to have another step, which is, I don't know, assign home for arg, and then that's going to get argument, which is going to be a var.argument. Yeah. And it's going to receive the home list of homes, and that's going to return x86. So it's going to delegate. Come on, Sean. You can tell I'm running out of steam. So we'll delegate for each of these arguments and thread that through like we've done in previous cases. And then we'll handle all this. So let's jump down a level to this one. So dref, this is what? Is it register offset? Register offset. So we know that this one doesn't have any change to it. So we can go x86.dref. And again, we're just doing translation here. Homes. Except we need to translate the register. So let's say translate register, and we'll make a function for that. Immediate is a value, and we just do x86.immediate for I, and return homes unchanged. And this is a register, and we'll do this translate register again. So like we're kind of going through the pain that we would have to do in the other phase right here. And then here we're going to call, this is v, we'll call assign home for var. That's going to take v homes. Okay, so we've kind of delegated that. Here we can do x86.addq, and we'll do this translate register in a second. This is going to be assign home for arg, and that's going to take a, except we're going to have to do let new a homes a is that, let new b homes b, same thing but for b. And we need to pass homes here, and we pass homes a here, so we're threading it through. And then we return, and I've kind of reversed the arguments here, so I may flip them if possible without too much work. So we've got homes b, then we've got add q, new a, new b. And these are going to be, let's really quickly do that translate reg. That's going to be var.register, and it's going to return an x86.register. Case input. And I'll just, let's see if I can do I can never remember how to do that. Is it Control Alt, Shift Alt? No, Shift Alt duplicates. No, I'm trying to do column select. How do we do that? Control. Command Alt arrow key. Okay, there we go. So I'm going to copy this, paste it, and then I'm going to select that and type x86. Okay, so there's our translator. Super dumb, but I didn't have to type too much. Okay. Okay, let's finish up this function, and a lot of this is going to look similar to this. This is going to be move queue, right? Except we don't have B. Okay, and this is going to be the same pop queue. Pop queue. And push queue is going to be the same as that. Push queue. Okay, and then sub queue is going to be the same as the other two argument ones. And we'll have sub queue. Okay, before we go on and test this, which I think should be our last thing today, I think I want to clean this up because I've got order of arguments flipped in some places. Like this returns I want to flip these. And we'll flip these. Except, let me see if there's another function in the list module that we can use that has an accumulator that you supply but does not get returned. I don't think that that's a thing. And we want to, that's all right. Okay. Okay, we don't care about the state of the accumulator at each stage. Scan was getting closer, though. No, we don't want transpose. Okay, and that the reduce is an optimized version of fold where the accumulator and the value type or the item type are the same. I don't care about that. Map to. Nope. Fold right, fold until. Yeah, that's not what we want. We don't need to terminate early. You don't need to group by a key function. You don't care about the index of the element. Don't need to interleave or intersperse. Not using key find, key pop, key set, etc. Okay, I think this is probably, yeah, we don't have we don't have any need for a result in here, so I don't think that that's necessary. Let's look at Gleam pair. Oh, there's first. All right. Let's revert this particular change. What? Okay. I think what I want this to do is I just want it to be consistent, right? Because I have some of these backwards. And I think that's just going to serve to confuse. And same here. And we're going to have to fix a bunch of spots. I'm sorry, this is going to be tedious. But then things will line up better. Okay, and then up here, V, and I need to flip these. Okay, and then we're going to go up here and we have to flip these in a lot of places. You know, it's probably not strictly necessary to do this. I just feel like there's Yeah, you're right. Isaac, you asked, wouldn't you need the accumulated homes to generate the function stack frame setup and teardown? So fold seems fine. Yeah, we're probably going to use it at some point. We're just not doing it at this phase. And there was a note I read earlier, like frames need to be a multiple of 16. Right, so it says, in the process of assigning variables to stack locations, it is convenient for you to compute and store the size of the frame in bytes in the info field of the x86 program node with the key stack space. So we didn't have an info field in here, and maybe we should go ahead and stuff it in there. Anyway, it says that is needed later to generate the conclusion of the main procedure. x86-64 standard requires the frame size be multiple of 16 bytes. So like 2 words. Okay, and I need to flip these. And flip these. The other thing that I was thinking here is it kind of feels like if I did this well, there might be a possibility that I could thread these. Like I could do homes, pipe it to assign home for arg A, and then like map pair map right this, that sort of thing. Maybe when I get these all flipped, we can try that on some of them and see how it works. Here, I'm just gonna do like that. And I'm just gonna copy these because I've got patterns already. Okay, now quit complaining. You don't like to alias the homes threading? Let me show you. Let me show you what I was thinking. So let's start with add queue, and I'll comment this out, and we'll rewrite it. So I might do homes, pipe to assign homes for arg A. And there might be a yeah, except I need that to go through. Never mind. I thought it was going to be all cool, but it isn't. At least not for these two argument ones. So like for the single argument ones, we could do homes piped to assign home for arg A, pipe that to pair dot map second, say 6.negq. We could do that. Oh, I see what you mean. Like that's more for me making sure that I reuse, or I don't reuse something accidentally. Old Erlang habit, I suppose. But that's just so I make sure that like I've got the new result here, and I'm threading it into the next expression. So alias the name. Yeah. Yeah, I could see why you would suggest that. Anyway, I think let's see if this obviously the compiler is working. Let's go from one of our tests. I think we're ready to test this, except that we are not letting this escape. Maybe we want an int here. Like you mentioned, to get the stack size offset. I don't know. Let's leave that. I want to try to see if we generate the right instructions first, and then we can work on getting that the size of the stack frame out. Okay. Because we don't even have it in here. The other option is that we could give, well, but the block doesn't care about the. It's just a list of instructions. All right, let's make a test, and then we can call it a day. And I think we might use some of this. Yeah, let's use this. These things will be easy to figure out what the results should be. So import glee unit should, and we want that as var, and we want import langs x86 int as x86. We'll have assign homes test, and we'll have assign homes neg, just so we can use both of those programs. Right? Okay. And then I'm going to come over here, and I'm going to take this. Okay, and this is not going to be here. Okay, and we need import Gleam dict. Okay, and let's see if we can rename symbol on that. Nope. Rename symbol. All right. We will just search and replace x86. Let's go ahead and get the other example in here before I do that, so I can just copy. Assign homes test. Okay, let's do replace x86 with var. Okay, that actually replaced more than I wanted. Okay, but now it's fine, and we can go import langs x86 int as x86. Okay, and this can be VP, and that was wrong. You correct that. I don't know why we need this extra, name on it, because we're qualifying those with modules all the time. Oh, shadowing, not aliasing. Okay, yeah, I understand what you mean, and it's fine to shadow. Maybe it would be easier to read that. I think that was just a pattern that I'd done before, so I stuck to it for better or worse. Okay, so now let's do the manual translation. So we want to do the x86 program is this. Okay, and we have start again. x86 block. We have a move queue. And here's where the magic happens. So we know that this is the first variable we've encountered. Sorry, this is x86. Not immediate. So this is going to be a deref RBP -8, right? And then we'll do immediate 22 deref of -16, because that was a new variable introduced. And then we're going to do, we know that we're moving x2, which is the first variable, so we're moving -8. This is not an incredibly efficient program. We should have put Y3 into RAX, but you know, whatever. Okay, so now we've got another one on top of that, so that would be 24, right? So that's Y3 is 24. And then we have an add queue. So we're adding X1, which was given 16. And we're adding that to Y3, which was given 24. A little tedious, but we're almost there. A move queue. So we know that this is dref -24. So there's our address of Y3 into reg. RAX. And jump conclusion. Okay, so that's what this should do for this. So if we do VP and pipe it to assign homes, and then we say should equal XP. Okay, so let's run that test, see if we got our right answer. Fine. Okay, so that's just complaining about the other function here. So that passed. That's good. Let's do our last one, and then we'll call it a day. We'll make a commit. Okay, so this is our var x86 var program, and I'm gonna copy paste because this is not changing the number of instructions, it's just changing the language that they're in. So this will save me a little time. And this is gonna be x86 block, x86 move queue, x86 neg queue, x86, and so forth. Okay, so the immediate variable, and we're gonna probably copy from up here because I don't want to type all these derefs all the time. So we move 10 into that spot, we neg queue that spot, and then we move into RAX, and we add queue RAX that. This needs to change to x86 everywhere. So that the types line up. Okay, and then we'll do the same thing we did up here. And let's Gleam test. Okay. That's looking pretty good. So now we have all of our variables as stack locations at the end of assign homes. Again, chapter 3 is about register allocation. So we will we'll cover that later. And I think next week we'll cover patch instructions and generate prelude and conclusion, and we'll be basically done with chapter 2. We might consider doing some of the challenges that are in 2.11, as well as going back through and making sure, you know, some of these things I've deliberately skipped over, that we at least cover those things that are being talked about. And I'm getting the feeling that, you know, for this info field that they keep talking about in the text, it's really an association list between, you know, a string key and whatever, which to me screams that should be a struct, right, in Gleam. So what we might do is go back through those sections for all the things that they've defined what the info is. Let's make that a field in the program struct. Type that field properly. And then we can do things like record the max offset, right? And put that into the x86 program as the, for, or maybe even for each block, this is a thing on the block, this is the frame size. So that's something to think about. Anyway, let's make a quick commit and then we'll call it done for today. What has changed in... Yeah, we pulled out assign homes. Okay, add that. We added assign homes. We added assign homes test. And this is chapter... What were we in? 2.8. Assign homes. Commit. Push. All right. Thank you for coming today. Thank you, Isaac, for your feedback and catching me a couple times. And we'll see you again next week, hopefully.